Yeah.
Yeah, all right. Our next speaker is Yuval Dagan, talking about joint work with Ohad Shamir.
Thank you. I present the paper called Detecting Correlations with Little Memory or Communication, where correlation corresponds to correlations between features, and communication corresponds to the setting where the data is distributed between multiple machines, and the communication between them is costly. Okay, so let's start with some motivation. So we believe that it's important to consider computational bounds on practical machine learning settings as bounds for runtime, memory, and communication, as opposed to the most common bounds, the statistical bounds on data requirements. And this is really important when there's a lot of data to have efficient algorithms. Additionally, we will focus on practical machine learning settings as opposed to settings which are very important for the complexity community. And in this talk, we will talk about lower bounds on memory and communication for correlation detection. Okay, so let's present the setting using an example. And that's a variant of the light bulb problem, for those of you who are familiar. So assume that you get multiple samples of people. And for each person, you get multiple features. Their age, their happiness level, their hours of sleep, and their office hours. And your task is to find the pair of features with the highest correlation. Here, the highest correlation is between the sleep and office hours. Now, you assume that the samples arrive in a stream, one after the other. And there's a limitation in memory, so there's not enough memory to store all the samples at the same time. But you're allowed to perform multiple passes over the whole data set. So here's a trivial algorithm which finds the maximal correlation. It just estimates the whole covariance matrix from the samples. Here's an illustration. The data arrives, the covariance is being estimated, and then the largest correlation is being output. Now, this algorithm requires memory which is quadratic in the number of features, and one pass over the data suffices. And additionally, in order to get an epsilon optimal pair, you need roughly 1 over epsilon squared samples. Now, what can you do if you have less memory? So you can still find the correlation, but you'll need more samples or data passes. For instance, if you have just a little bit of memory, then you can perform d-squared data passes, and in each data pass, you can estimate one covariance entry. And this way, you can find the largest correlation. And if you have less data passes but more samples, you can do a similar trick. And this algorithm works whenever the memory times the sample size times the number of data passes is roughly the number of features squared over epsilon squared. Now that's a trivial algorithm for this problem. And the question is it possible to do better? And we show that, in general, the answer is no, if the error epsilon is very small. So here's the theorem. Assume that you get samples from a divariate Gaussian distribution, where each sample corresponds to a person, and the d coordinates of a sample are the features. And assume that the coordinates are independent, except for one pair with a small covariance of epsilon, where epsilon is at most d to the minus 3. Then any algorithm which finds the correlated pair requires an amount of memory times sample size times data passes to be at least the number of features squared over epsilon squared. Now, indeed, the requirement for epsilon is very strict. Epsilon has to be small. But we still think it's interesting because most algorithms work for any value of epsilon. And also, we hope that this requirement can be relieved a little bit. So here are some generalizations for this setting. So in the case where you want to find correlations between more than two variables, between R variables, a similar theorem holds when you replace d squared with d choose R, where d choose R is the number of R tuples of features. And this means that in order to get close to optimal accuracy, using just one pass over the data, you need a memory of size roughly d choose R. And there are other generalizations that we can discuss in the poster session. So up to now, we've been talking about the streaming setting, where samples arrive one after the other. And now we'll move to talking about the distributed setting, where the samples are distributed between multiple machines. So each machine gets samples of multiple people, and now they have to communicate and find the largest correlation between features. And communication is costly, so we would like to minimize the communication. And here we show a tight bound stating that the total sample size times the average communication per machine has to be at least d squared over epsilon squared. And this is also tight. And this means that if you want to achieve close to optimal accuracy, each machine has to send data of the size of a whole covariance matrix. Okay, so we'll discuss a little bit prior works. There's a lot of very interesting prior work on memory lower bound for machine learning problems. And that's where we contribute. So most settings are either settings which are very interesting for the complexity community, but are not used in practical applications. And there are another lower bounds where in settings where there is not enough memory to store one sample. And we show a lower bound which is quadratic in the dimension. And yeah, there is a lot of future work, and that's it.
Thank you. Are there any questions? Not? Thank the speaker again.